In April of 2026, engineers at NASA's Jet Propulsion Laboratory made a decision nobody on the Voyager mission wanted to make. They sent a command, one that would take more than 23 hours just to arrive, telling Voyager1 to permanently shut down one of its last remaining scientific instruments, an experiment that had been quietly running almost without interruption since the year the spacecraft launched. It was not a failure. It was a sacrifice, a calculated trade meant to buy the spacecraft. A little more time before its dwindling power supply forces an even harder choice. What is left running on Voyager 1 today is almost nothing. 2 instruments out of the 10 it once carried, drawing on a power source that loses a little more strength every single year, with no way to ever refuel or repair it across 15 billion miles of empty space. And yet, using nothing more than those 2 remaining aging sensors, Voyager 1 is still sending back numbers that do not match any model of interstellar space scientists had before it got there. Numbers that, according to the physics built before this spacecraft ever crossed into the region it currently occupies, should not exist in the way they do. This is the story of what Voyager 1 is actually measuring right now in the region of space it entered years ago and is still traveling through today. And by the end of this video, you will understand exactly why engineers just switched off part of a nearly 50-year-old spacecraft to keep it alive, what its 2 surviving instruments are still detecting that nobody predicted decades ago, and why the next few months of this mission may be more scientifically important than almost anything Voyager 1 has sent back since it first left Earth in 1977. Let's start with where Voyager 1 actually is, because the numbers involved are almost impossible to hold in your head without a comparison. As of 2026, Voyager 1 sits more than 15 billion miles from Earth, moving away at roughly 35,000 miles per hour, a distance so vast that a radio signal traveling at the speed of light, the fastest anything in the universe, is capable of moving. It takes over 23 hours to complete the one-way trip. On November 18th, 2026, at 2:16 and 7 seconds in the morning Pacific time, Voyager 1 will cross a threshold no human-made object has ever reached before, a distance of exactly 1 light day from Earth, so far away that a signal sent on a Monday would not arrive back on Earth until Wednesday. 2 full days lost simply waiting for light to finish the round trip. Voyager 1 launched on September 5th, 1977, on a mission originally expected to last 4 or 5 years. A simple tour past Jupiter and Saturn before drifting quietly into retirement somewhere around 1981 or 1982. Instead, it kept going, flying past Jupiter in 1979 and Saturn in 1980, and in 2012, 35 years after launch, it crossed the heliopause, the outer boundary of the Sun's protective bubble of solar wind, becoming the first human-made object in history to leave the solar system entirely and enter true interstellar space, a place no spacecraft, no probe, and no instrument built by human hands had ever physically reached before. Here is what makes that crossing matter so much, even now, well over a decade later, with the spacecraft still limping along on borrowed time. Interstellar space is not simply more of the same emptiness that fills our own solar system. It is a genuinely different physical environment, filled with the leftover material from exploded stars, threaded through with the galaxy's own magnetic field, existing under conditions no spacecraft had ever directly sampled before Voyager 1 arrived. For decades before that crossing, physicists built careful, peer-reviewed models predicting what that environment should look like. Models based on theory, on indirect observation from telescopes, on decades of careful extrapolation. Those models generally agreed on one thing. Interstellar space, at least in the immediate neighborhood surrounding our solar system, should be relatively calm, thin, quiet. A cold, sparse medium where charged particles drift slowly and not much of anything dramatic happens. Voyager 1 did not find that. Starting in 2017, the spacecraft's plasma wave instrument, the same one still operating today, began picking up something researchers had not predicted and could not immediately explain. A persistent, narrow band signal, a kind of faint but continuous hum in the surrounding plasma that, according to the physics built before Voyager 1 got there, simply should not have been present in the way it was. Not a single spike that could be waved away as a glitch or dismissed as instrument noise from a spacecraft nearing its 50th birthday. A continuous, sustained signal, recorded year after year, stretching across a region of interstellar space more than 900 million miles wide, roughly 10 times the distance between the Earth and the Sun, a scale that made it essentially impossible to explain away as some kind of localized fluke. Researchers analyzing the data, published in the peer-reviewed journal Nature Astronomy, concluded that the region immediately surrounding our solar system is not the quiet, uniform void the earlier models had described. It is turbulent, structured, and active at scales ranging from mere meters up to distances measured in millions of miles, a level of complexity that was completely invisible to every model built before humanity had an actual instrument sitting inside that environment to measure it directly, rather than simply theorizing about it from the safety of our own solar system. Before we get into exactly why the signal is still considered an open scientific mystery even now, nearly a decade after it was first detected, if the idea of a 50-year-old spacecraft quietly rewriting the physics textbooks from 15 billion miles away is the kind of story that keeps you watching until the end, go ahead and subscribe now, because what Voyager 1 found at the actual boundary of the solar system back in 2012 is even harder to reconcile with what scientists expected. For decades, the standard model of the heliopause, the boundary separating our solar system from interstellar space, predicted a slow, gradual transition, solar wind fading out gently on one side, interstellar material becoming detectable gradually on the other, blending together the way a river slowly merges into the sea rather than crashing into it. That is not what Voyager 1's instruments recorded when it actually crossed that boundary in 2012. Instead, the spacecraft measured particles slamming into each other at extraordinary speeds, generating temperatures approaching 30,000 degrees Celsius in a region of space that models had predicted should be comparatively cold and calm. Colder even than most of the already frigid outer solar system it had just spent decades crossing. Researchers have described this region in published papers as something closer to a wall of energetic colliding particles than a gentle transition zone, a genuine, measurable barrier that current theory did not fully anticipate, sitting right at the edge of everything humanity had ever directly explored before. Layered on top of that came an even more fundamental surprise involving magnetism, one that struck at a much deeper assumption about how our solar system relates to the rest of the galaxy. Before Voyager 1 crossed the heliopause, the standard prediction held that the Sun's magnetic field and the wider galactic magnetic field should be almost entirely separate systems, distinct environments meeting at a clean, sharp boundary with little meaningful interaction between them, two separate bubbles simply sitting next to each other. What Voyager 1's magnetometer, its other surviving instrument, actually recorded was different. The magnetic field lines from the Sun's own extended influence and the magnetic field of the surrounding galaxy appeared to be connected, interacting through a process called magnetic reconnection, in which field lines from separate sources rearrange themselves and release energy in the process, the same basic physical mechanism responsible for solar flares erupting from the Sun's own surface. Rather than existing as two cleanly separated magnetic systems, our solar system and the wider galaxy around it appear to be linked, exchanging energy across the boundary in ways no model built before this crossing had accounted for, a finding that suggests the shield protecting our entire solar system from the harsher radiation environment of interstellar space may behave in ways still not fully understood. None of this, to be clear, is evidence of anything beyond known physics, and no credible peer-reviewed research on Voyager 1's data has ever suggested these readings point to anything artificial, extraterrestrial, or outside the laws of physics as we currently understand them. What it actually represents is something almost more interesting, a direct demonstration that our theoretical models, built entirely from the outside, using telescopes, mathematics, and careful extrapolation, were incomplete in ways nobody could have identified without an actual instrument physically present in that environment. The phrase breaking physics, in the way scientists working on this data actually use language, does not mean the fundamental laws of the universe have been violated. It means the specific, detailed predictions built from those laws, applied to a region of space nobody had ever directly sampled before, turned out to be wrong in specific, measurable ways, once real data finally arrived to test them. This is exactly why the decision NASA made in April of 2026 carries so much weight. Voyager 1 relies on a radioisotope thermoelectric generator, a device that converts the heat produced by slowly decaying plutonium into usable electricity, and that decay happens at a fixed, unstoppable rate. No engineering decision can pause or reverse, no matter how carefully the team manages everything else on board. Both Voyager spacecraft lose roughly 4 watts of available power every single year, a slow, steady drain that has been quietly shaping the entire second half of this mission, forcing harder choices with every passing year as the available margin keeps shrinking. On April 17, 2026, engineers sent the command to permanently shut down Voyager 1's low-energy charged particles instrument, an experiment that had been running almost continuously since the spacecraft launched in 1977, measuring ions, electrons, and cosmic rays streaming in from both our own solar system and the wider galaxy beyond it, data that had helped researchers map pressure fronts and density changes across the boundary of interstellar space for nearly 5 decades. The decision followed an unexpected power drop detected during a routine roll maneuver in late February, a warning sign that pushed engineers to act before the spacecraft's automatic undervoltage safety systems could be triggered on their own, a scenario that would have required a lengthy, risky recovery process with no guarantee of success given the spacecraft's age and the communication delay involved. As Voyager mission manager Kareem Badruddin put it, Shutting down a working science instrument was nobody's first choice, but it was the best option available to protect everything the mission still had left to give, preserving the two instruments still, capable of studying the strangest, least understood environment the spacecraft has ever passed through. What remains operational on Voyager 1 today is genuinely down to the bare minimum, just two instruments: the plasma wave subsystem responsible for detecting that mysterious, persistent hum, and the magnetometer responsible for tracking the unexpected magnetic connections at the boundary of our solar system. Of the 10 original instrument packages Voyager 1 launched with in 1977, 8 have now been switched off. Each shut down a carefully planned, years in advance decision made by a team of scientists and engineers who long ago sat down together and mapped out exactly which instruments to sacrifice and in what order, to squeeze as much remaining science as possible out of a shrinking power budget, knowing full well that once an instrument goes dark, there is no way to simply turn it back on if the decision later turns out to have come too soon. It is a strange kind of engineering, planning years in advance for a slow, deliberate ending, choosing precisely which questions will go permanently unanswered so that others can keep being asked for just a little longer. But the team has not simply accepted that shrinking budget as the final word on this mission's future. Engineers are currently testing an ambitious, experimental power-saving procedure internally nicknamed the Big Bang, an attempt to restructure how electricity flows across the spacecraft's remaining systems in order to recover additional usable power from components that are currently running less efficiently than they could be, squeezing extra capacity out of hardware that has already been operating far beyond its original design life. Because any change to a 50-year-old spacecraft with no manual or override and no possibility of repair carries genuine risk, the kind of risk that could end the mission permanently. If something goes wrong, the team chose to test the procedure first on Voyager 2, which has slightly more power in reserve and sits somewhat closer to Earth, making a potential failure less catastrophic for the overall program. Those tests were scheduled for May and June of 2026. If they succeed, the same procedure will be attempted on Voyager 1 no earlier than July. And if that attempt also succeeds, there is a real, if cautious, possibility that the instrument shut down in April, the one that had been quietly measuring charged particles from the galaxy for nearly half a century, could eventually be switched back on, restoring a third working sense to a spacecraft that has already learned to make do with less than it once had. All of this is happening against the backdrop of that approaching milestone in November, the moment Voyager 1 crosses one full light day of distance from Earth, a threshold no human-made object has ever reached while still alive, still transmitting, still doing science, a marker that will stand in the history books long after every engineer currently working on this mission has retired. Every hour that passes after that date adds roughly 38,000 more miles between the spacecraft and home, steadily stretching the communication delay in both directions, a gap that will only continue to widen for as long as Voyager 1 keeps functioning at all, drawing the mission closer year by year to the moment its last watt of usable power finally runs out for good. What makes this moment genuinely significant beyond the raw numbers is the simple fact that Voyager 1 remains the only functioning scientific instrument humanity has ever placed directly inside interstellar space, the only living witness we have ever had to what actually exists out there rather than what we assumed must exist based on theory alone. Every telescope on Earth, every satellite in orbit, no matter how powerful or expensive, is still observing that environment from the outside, filtering everything through models built from a comfortable distance of many billions of miles. Voyager 1 is inside it, sampling the actual plasma, the actual magnetic field in real time, as it physically moves through material that formed long before our solar system existed, material that no future mission will be able to sample again for at least a generation. That is precisely why the persistent plasma hum discovered in 2017 remains such an active area of research nearly a decade later. Scientists still have not fully determined whether that signal comes from thermally excited plasma oscillations, a phenomenon that would fit inside existing physics without requiring major revision, or from a related but distinct process called quasi-thermal noise, one that would require meaningfully updating how researchers model the interstellar medium going forward. Settling that question requires either more data directly from Voyager 1, which is producing less of it every year as instruments go dark one by one, or an entirely new mission built specifically to study interstellar space, and no such mission currently exists or is funded anywhere in the world. If built and launched today, the next spacecraft capable of reaching the same boundary would not arrive there for at least another 25 years, leaving a long, uncomfortable gap in humanity's direct knowledge of this environment. So, to bring this back to where we started, no, nothing about Voyager 1's reading suggests contact with anything beyond known natural physics. What its instruments are actually detecting is something quieter and, in its own way, more remarkable, direct evidence that the space immediately surrounding our solar system is more turbulent, more structured, and more magnetically connected to the wider galaxy than any model built before the spacecraft arrived had ever predicted. The specific numbers Voyager1 is sending back genuinely do break the physics we expected. Not the laws of the universe themselves, but our best previous understanding of what those laws should produce in a place no instrument had ever measured directly before. That, honestly, might be the most quietly remarkable part of this entire story. A machine built using 1970s technology, running on less power than a household light bulb, missing 8 of its original 10 instruments, is still teaching us something new about the universe using only a plasma detector and a magnetometer, the two simplest, hardest working tools left on board. The scientific equivalent of an explorer who lost most of their equipment along the way but kept walking anyway, still taking notes with whatever was left in their pockets. Every additional month that survives is another chance to refine our understanding of a boundary. Humanity may not get to study directly again for decades, since no replacement mission capable of reaching this same distance currently exists, and building one from scratch today would take a generation just to arrive where Voyager 1 already sits. And whether or not the Big Bang procedure succeeds this summer, whether or not that shutdown instrument ever hums back to life, Voyager 1 will keep moving forward regardless, carrying its golden record and its 2 remaining working senses deeper into a galaxy that, even now, still has more surprises left to give us than our models ever predicted. One faint plasma reading and one quiet magnetic measurement at a time. There is something worth sitting with in the fact that the very numbers making headlines as breaking physics are, at their core, simply Voyager 1 doing exactly what it was never specifically designed to do, teaching scientists back on Earth that the universe, immediately beyond our own front door, is stranger, more dynamic, and more tightly connected to everything else than anyone building those original models in the 1970s could possibly have guessed. If this kind of deep dive into what real, published data from humanity's most distant spacecraft is actually telling us is what you come here for, make sure you like this video and subscribe to the channel, because Voyager 1 is not finished yet, and when the next reading comes back, we plan on being here to break down exactly what it means.